Welcome to this PowerPoint with commentary intended to illustrate calculation of a correlation using some example data, primarily intended for students of Psych 325, Victoria University of Wellington in 2010. Okay, this is the data I'm going to be using, thanks to this website for providing it. This data, as you can tell just by looking at the figure, seems to indicate that as the number of pirates operating has decreased, global average temperatures have gone up, and the point of this exercise is to calculate and see exactly what the level of that correlation is. Now, the first thing that we need is a formula for calculating the correlation, and there are a variety of different versions. This one here, for example, is really useful if you can either calculate easily or already have available to you the standard deviations for the two data points. So in this particular case, X refers to the number of pirates, Y refers to global average temperatures, and what we're looking to do is to see whether or not there's any relationship between the two. Remember, the important thing here is sigma. If you've forgotten your statistical notation, sigma just indicates the sum of. In this case, I equals each of the numbers of pairs of data. So we start at 1 and we go up to n. In this case we have 7 data points, so x minus x bar means subtracting the mean of x, or the mean number of pirates, from the number of pirates for the first, second, third, fourth, fifth, sixth, seventh data point. Same thing applies for y. Now I'm going to work through a calculation which actually uses a different version here. This doesn't require you to know what the standard deviations for the different things are in advance, but essentially the same general rules apply. Okay, here's our data. 7 data points for each of these different years. What I need to do is to calculate each of the different bits that appear in the formula. So for example, I need to know what the square of the number of pirates is. Well, here it is for each of the 7 time periods. I also need to know for y, for example. So that's what I've done. This sheet here shows each of the different bits that we need for the correlation calculation. So, for example, we need to know what the sum of x times y is. Here we have x times y for the first time point, x times y for the second, third, fourth, fifth, sixth, seventh. Because this is the sum of those, we add them all up, and that gives us this number here, 1,735,000. We also need the sum of x and the sum of y, and that's pretty straightforward. So we just sum up the number of pirates across the 7 time points, that's 120,000. The sum of global average temperatures across the 7 time points, that's 104.3. As indicated earlier, we also need the sum of x squared. In this particular case, sum of x squared is the sum of 35,000 times 35,000 plus 45,000 times 45,000, so on and so forth, to get all of these numbers. And then we add them all up. That gives us the figure here. We also need the sum of pirates squared. Not the same thing. Okay, so this is the sum of the number of pirates, 120,417, squared, which gives us this unfeasibly large figure here. We need to do the same thing for y squared and sigma y squared, represented here. It's exactly the same as we've just seen for the x part of the equation. Now, bearing in mind our original formula, we now need to actually insert the numbers that we've generated here into this equation. So, let's start with the top line. We need n times the sum of x, y. We have 7 data points, so we multiply our sum of x, y by 7. It gives us 12 million. We also need the sum of x multiplied by the sum of y. Again, something like 12 million. Then we subtract one from the other. So, subtract this unfeasibly large number from this almost as an unfeasibly large number, and it gives us a difference of about 400,000, minus 400,000. That is the number that corresponds to the top of our equation. We now need to calculate each of these separate bits here. Again, fairly straightforward. We need to know the sum of x squareds multiplied by n, the sum of y squareds multiplied by n. We take those out of our table, multiply them by 7. We then subtract sigma x all squared from the number that we've just calculated here, and the sum of y all squared from the number that we just calculated here. Work through it, that gives us a massive number. Ultimately, when we work through it, this produces the number on the bottom of the equation. Notice that they're starting to get closer and closer. Minus 407,853 divided by 442,480.8223, and that gives us our correlation value, minus 0.922 in this particular case. But what does it actually tell us? Now we need to have some kind of criterion against which to test that correlation. How big does it need to be in order for us to say, well, the odds are relatively small that this particular correlation coefficient could have occurred by random variation? And to do that, we need a test of significance. Before we can do that, we need our degrees of freedom. That's an indication to not just, if we're doing the statistics package, but also to the reader. It's a modified indicator of the sample size. Remember, the larger our sample, the more confident we can be that the number that we've got approximates what we would get if we had the whole population, if we had every year, for example, data for number of pirates and global average temperatures. So, in this case, degrees of freedom is always, for a Pearson's correlation, the number of observations minus 2. We have 7 observations. Subtract 2 gives us 5. It should be a small r. And what we do now is take these two pieces of information, the degrees of freedom and the magnitude of the correlation, and look at a table of critical values for r. Now, in psychology, our default value for significance, or assuming something is actually meaningful, is p less than 0.05. 1 chance in 20 that it could have occurred due to random variation. If we look down this far left column here, this is where we look for our degrees of freedom value. In our case, we have a value of 5. We're also interested, if we're looking at that default level, at the 0.05 column, and we look down here until the two meet. For 5 degrees of freedom, a significance level of 0.05, the critical value of r that our correlation needs to exceed is 0.75. Or of course you can use SPSS. Now in our particular case, our correlation is 0.92 in magnitude, it's larger than 0.75, so that tells us that our correlation is statistically significant at p less than 0.05. In fact, if we were to look at p less than 0.02, the critical value there is 0.83. Again, 0.92 is still larger than 0.83, therefore our correlation is significant at p less than 0.02, and indeed at p less than 0.01 as well, but not at p less than 0.001. 1 chance in 1,000 that it would be due to random variation. In fact, our actual significance level is somewhere around about 0.003. It falls somewhere between these two. Calculate it in SPSS using this series of button presses, and you end up with this output here. What we're particularly interested in looking at here is our correlation is identical. The actual significance level is 0.003, which is why on the table of critical values it falls somewhere between the p less than 0.01 and p less than 0.001, which is less than this. And we also have an indication here of our variance. Now, I hope that was helpful. Thank you very much.